I'll give it a.
For the audience members that are here, we're just waiting a minute or so for people to trickle in before we start the session. But you can start typing in the chat.
All right, let's go ahead and kick things off. Hey, everybody. I'm welcome to the general track. I'm Matt Haberland. I'm here with my co-host, Medican Monk. And the focus of the general track is basically anything that doesn't fit into other tracks. I want to let you know if you have a question during the talk, you can find over above the chat window, there is a raised hands tab, and you can click on that raised hands tab and raise your hand. And in order to come up on stage after the talk is done and ask your question. There's also the option to click on the Q&A tab, and you can type your questions out there, and we'll read those off at the end. So yeah, without further ado, our first speaker today is Simone Baccio.
Hello everyone. Thank you, Matt, for the introduction. I'm very excited to be here. It is my first time at the SciPy conference, and I will be opening the general section. And by presenting to you a new tool we have ported to Python, this PyRSB, and it's a work I did in collaboration with Michele Martone. We both work in the field of HPC, of high performance computing. Michele Martone works at the Leibniz Supercomputing Center, that is one of the big HPC facilities in Europe. And on my side, I'm a computational scientist at the Cyprus Institute. The purpose of PyRSB is to provide you portable performance on multi-threaded sparse BLAS operations. Here it's a short overview on the talk. We will have a brief introduction on the scientific background of the problem. I will introduce the recursive sparse block format, that is the format that is brought to Python by PyRSB. I will talk about PyRSB itself, which is an interface to libRSB, and show some performance results. So I don't know how many of you are familiar with the concept of sparse matrix, and therefore we start now with some introduction to the mathematical and scientific background of it. As the name says, the sparse matrix opposes to a dense matrix by being sparse. So most of its components, as you can see here in the figure, are zeros. Here, the black squares are the non-zero components, while the white, what is white, are zeros. A dense matrix instead will be full of elements. So there is no strict definition for a sparse matrix, but it's mostly a matrix whose most components are zeros. Or another definition that I like that is more HPC oriented regarding the scaling of their application is a matrix where the non-zero components scale with the size of the matrix and not with n squared, which is the surface of it. So why these metrics are important? Well, on one side, as you can see, their application can be highly optimized by taking into account only the non-zero components. And therefore, out of these, there have been produced several algorithms that are used for specific calculations, like there are iterative linear solvers or iterative eigensolvers. These are iterative algorithms where the matrix will be applied several times. And there are many ways of representing them, and the RSB format, the topic of this talk, is one of these is an hybrid layout for cache-based multi-core CPUs. So now just a short overview where this sparse matrix comes from. One side from a scientific application is the case of discretization of partial differential equations. Partial differential equations are these very complicated equations in physics that describe the motion and describe how physical systems evolve. So if we take the case of a grid like here, a differential equation will be discretized by taking the difference of the value of the function between two neighboring points. And this gives straight away gives a sparse matrix where here these are representing the connection between two neighboring sides. A similar image you would have it in finite elements, where though the grid is not regular, and therefore one will get a sparse matrix that is much less regular, like the one here. Another situation where sparse matrices arise are in graph theory. And as an example here, we have the state map of Netherlands, which connectivities give these beautiful sparse matrix, which represent the connection between 2 points on the map. So one is putting the edges as a vector, and the connections are the non-zero components on this matrix. Here again, it's plenty of algorithms that take advantage of the sparsity of this matrix and compute fast some properties of the system, like the shortest path between 2 points, the maximum flow, etc., etc. So, as I said, there are several ways of representing these sparse matrices. One case, it's the simplest, it's the coordinate format. In this case, one is listening the value of the non-zero components, and then the coordinate, like the name says, of the row and column elements. So these are the coordinates where the non-zero components are. These, in this situation, will give rise to such a sparse matrix. As you can see, as you can imagine, if for a bigger size we have many non-zero components on the same row, so the element I will be followed of the same values. And the way to compress it up is to use the compressed sparse row format, where the I is replaced by P, which is a non-zero incremental counter. And now, for instance, this is telling us that there are 2 non-zero components on the first row, and then the difference between the two numbers tells us the number of non-zero components on the second row, etc., etc. There are many sparse formats for one simple reason. One wants to obtain performance, and the interest for performance goes in 2 directions. One for efficient modification of the matrix, and this is very simple to do it with a coordinate format by simply adding a new element to the list, or for an efficient access and matrix operation. And this is what CSR offers, where by compressing the row indices, it's much faster to apply it. So the purpose of our work is to improve the performance, the application performance of these matrices. And the performance is important because, as I said before, there are many algorithms that use that exploit the sparsity of the matrix for computing fast calculations. And these are, for instance, iterative solvers, where one would apply the matrix several times against a vector. This is an algorithm, for instance, used for computing the solution of a linear system, that is dx equal b. B is our right-hand side, x is the solution. And by solving this linear system, one obtains the inverse of d against this right-hand side. This is done recursively. You can find such algorithm in SciPy.sparse.linear algebra. And you can see that, for instance, an algorithm like GMRES, by solving a linear system, applies many, many iterations, increasing the accuracy of the solution. These are presented with the accuracy by taking the difference of the 2 components. So many iterations are required. Many application of the sparse matrix is required for solving this linear system, and therefore the performance on how fast we do it is critical in our algorithms. For this, we have many tools in Python, like we saw SciPy.sparse offers various representations of the matrix format. The difference performance is significant. You can see it here, a comparison between the CO and the CSR or CSC format. And otherwise, if one wants to go on GPU, CuPy offers also sparse matrix representation. And if you don't have a matrix, but you have a sparse array, you can use on PyData. By PyData, you can use the package sparse. Now, what we are bringing to you is a new package for accelerating the application of sparse matrix on CPUs, and its name is PyRSB. This is a package that is compatible with SciPy, which by using the now RSB matrix format, one can have a significant acceleration on the application of the sparse matrix. So what is new? PyRSB offers portable performance on multi-threaded sparse BLAS operations. It can be installed via pip, and this can be done at the moment only on Unix-based operating system. For Windows and iOS, some more work is required, but coming soon. It offers an interface to the libRSB library, which objectives are to offer interoperability. Indeed, it is written in C, C++, as a Fortran interface. You can have it in Octave and Python. It's portable. No intrinsic have been used, and it offers great performance on any kind of CPU hardware. And it's compatible with other, an objective is to make it compatible. So we offer a BLAS interface, and right now we offer a PyRSB interface that is compatible with SciPy. We achieve high performance on CPU by using cache blocking and coarse-grained training, as I'm going to show you hereafter. So our target problem is to accelerate the application of sparse matrix against a dense matrix. The sparse matrix can be many properties where many of these are exploited by PyRSB. For instance, if the matrix is symmetric or Hermitian, PyRSB will store only half of the components. As well, if you want to perform transposer and transpose operations, also PyRSB is optimized for that. And it can work with the 4 BLAS types for the single, which are single, double, floating precision, complex numbers. And on the other hand, the dense matrix has also various specifications, like can be ordered by row, by column, and these are other details we can see after. But in details, what is the recursive sparse block format? So the idea here is to recursively halve the matrix in subdomains that optimally fit on the cache of our CPU. The cache is the cache memory. I'm sure most of you are aware with the concept, where the cache memory, it's a much reduced size. Usually it's of the size of few megabytes memory directly inside the CPU, which has very fast access to data, while on the other side, the standard DRAM memory has much slower access. So if we can fit the information about our matrix on the CPU directly, this provides a great performance. So by this, we reduce the block size, and then each block can be represented either with a CO or a CSR matrix representation. So the choice between the formats depends on the number of non-zero. The block size, as I said, it's reduced for optimal cache reuse, and the number of blocks allows for multi-threading. Indeed, we avoid race condition by then applying, as I have an animation just later, by applying blocks that act on different right-hand side at the same time. So there is also a tuning procedure that optimizes the size of the blocks, and also this I'm going to give more details later on. PyRSB is an interface to libRSB that is implementing all of these in C and C++. It's meant for HPC. It can handle very, very large matrices. It actually is here where the great performance is achieved. It's portable, free software. You can download it. This is the link. It offers its own interface in C, C++, and Fortran, Sparse BLAS interface, and now it's available on Python within PyRSB. So on one side, one may want to do operations with multiple right-hand sides. So our matrix, our target matrix, may have different size of columns. PyRSB supports both columns stored in row major format, which is in NumPy is the C ordering, the contiguous array, and supports also Fortran array format, which in NumPy is the F order. These two orders can provide different performance, and one may want to try out storing the right-hand side on the two different orders. Also, as I mentioned, it offers multi-threading. As you can see from this animation, many blocks can be active at a time. This is the situation where we have 4 threads, And each block, thanks to the subdivision to the division subdomains, it's acting on different components of the output. In this way, we're avoiding race conditions, and we are able to use multithreading in sparse formats that usually it's actually quite hard to achieve. So this is the number of threads it's implemented by OpenMP and can be managed by the flags that OpenMP provides. There is also a tuning procedure that optimizes the size of the blocks on the matrix one is going to use, and the number of blocks and their size is going to change according to the problem. So for this reason, the autotuning procedure needs to be done on the matrix itself and for a specific number of right-hand side or number of threads. This can be easily done by saying autotune. The matrix will be autotuned for optimal performance. And how the structure of the matrix is going to change can be either on the left, where we have much more blocks that is meant for more threads or smaller cache. Going to the right, we have a more coarse representation where the block size is larger, and this is meant for less thread and larger cache. Indeed, you can understand that here, when we have many threads, many blocks can be active at the same time with such a format, while less are allowed here. Now I'm going to show you some results, some numerical results. These have been applied to a large set of sparse matrices, because it's very important to test matrices that have different representations, and these are accessed these can be accessed in this online library of sparse matrices. And many are here. We focused on matrices of very large size because it's important for PyRSB to play a significant role compared to standard formats for the matrix to have a large size. And we tried many matrices of these. So for instance, you have problems that are coming from fluid dynamics, graphs like we saw before, matrices that have many different structures. All of these are numbered from 1 to 28. Here are some representations, and these are where the matrix where the results are going to be measured. The results have been measured on a supercomputer offered at the Leibniz Supercomputer Center. Its name is Beast. It's equipped with AMD GPUs that have 64 cores. We use 24 threads, and we compiled in an even manner both LibRSB and the SciPy library. Our results are going to be compared against the CSR matrix of SciPy, and we tested, in order to provide a complete overview of the potentiality of the library, against the 28 matrices, we've tested many formats and many data type. So we tested these various number of right-hand sides, ordering, and data type. So for each matrix, we have 32 numbers that will give to us such results. The plots that you see here are representing various information about our test runs. The whiskers here represent the range between the minimal and maximal values. The box is where half of the values we've measured are contained. These are, I remind you to you, are these 32 values. So these are, the box represents where half of the data is contained, and the line is the median. So as we can see, compared over CSR, thanks to multi-threading and the optimal performance, we achieve for a non-tuned RSB a speed up that can go up to an order of 65. And once we perform autotuning, you can see that there is a significant improvement. Most of the data are more grouped together, and our speed up goes from a factor of 10 to more than 80. So this is a great speed up compared to CSR. And if you have a scientific problem where you have to deal with sparse matrices of very large dimension, I would suggest you to give a try to our library. Here, it's another, just to give you an idea on the cost of the autotuning procedure. So going from the left to the right plot, here it's the speed up that Autotune has provided for each case. So this can provides a speed up for each case between 1 and 5. And these are the number of iterations one has to do, which means the number of times the matrix should be applied in order to amortize the cost of the autotuning. So it may cost significantly compared to the application of the matrix, but if you have to apply it many times, like order of hundreds, then it's very useful to give a try also to the autotuning procedure. So in conclusion, I've introduced to you a new tool, PyRSB, for sparse operation. It is HPC-oriented and multi-threading. It's easy to install via pip, and the interface is compatible with SciPy Sparse. We have widely tested the library, showing a speed up between a factor of 10 to 80 compared to a CSR. And it's critical for achieving this speed up the autotuning procedure. Now, our steps in the future are to extend the support for PyRSB to Windows and iOS. We would like to start to extend our performance studies, and we will work on reducing the cost of the autotuning procedure. So thank you very much for your attention, and I will give a start to the Q&A session.
All right. Thanks very much, Simone. That was excellent. I'm a SciPy developer myself and use sparse matrices, so very interesting. Okay, our first question today, I know you just addressed this, but let's try to address it specifically. How fast is the tuning? And yeah, can you speak a little bit more about that and how whether it requires retuning for each PDE or FE problem you're solving?
Sure. Okay. Let's address both questions. Maybe I will go to such matrix. So at the moment, what the tuning procedure is doing is there are two parameters, either to test. Either a quadrant should be halved again. So as you see, we proceed always halving the matrix. This is done for simplicity reason, because yeah, otherwise one will get in a too complicated fashion. And so we are always halving. So the autotuning procedure has to decide whether the quadrant should be halved or instead put back together. And then which format is best to use for the quadrant. So either CO or CSR. Others format can be supported in the future. So the tuning procedure is quite expensive because it's doing a kind of brute force around the minimum, trying to undo and doing the various steps. These can be significantly improved, and there are various ideas. For instance, an idea is to use machine learning for it, and by seeing the image of the representation, a machine learning procedure could automatically provide us what is the best solution. These are ideas that we are investigating. And so at the moment it's quite expensive, but there is a lot of space for improvement. And whether it needs to be done again or not depend on the matrix. This depends on the structure of the matrix itself. So if you have a problem like mine, where the structure of the matrix, I go back to this slide here, where the structure of the matrix, let's say, is regular, but only the non-zero components are changing, then you don't have to redo the tuning procedure. On the other side, if your matrix is changing by case by case, then yes, it's required to redo the autotuning.
Okay. All right. So next question is from John. Is there compatibility with? Can you see these on screen?
Yeah, I can see them. Yeah. I don't know in detail the specification of the two packages, so I cannot comment on that. We are compatible with SciPy Sparse, so we offer the RSB matrix that can be used in the same way. It works in the same way as SciPy Sparse matrix representation.
So I suppose if those can be converted to like a CSR format, then you could be.
Yeah, it can be initialized in various ways, either by providing directly a dense matrix or a CSR format, or as here by providing either this structure or this data structure. So yeah, I don't know if this replied the question, but I think it's the best I can do.
Okay, and next one, Python has a limitation of memory. Does this library have a limitation on array sizes?
Well, the memory, of course, okay, the library is written, so everything lives in C. Python is only interfacing to the library, providing the data to the library, but everything is standard software. And well, the limitation in memory depends on the memory available. I don't know if this replies the question. It's Matt, do you have a bet?
No, that makes sense. The memory available on your machine, right? There's not an inherent limitation in your software.
And also Python itself has not really limitation on memory can be used, I think. Depends. Yeah, anyway, okay.
All right. Those are the questions that I see. If there are others, please raise your hand very soon. Otherwise, we're going to, let's thank the speaker, give some of those emojis. If you want to speak with the speaker later, we have the Slack channel where you can find Simone. And yeah, well, thank you all for coming to the first session. And I'm going to go ahead and end it now. Thank you all for coming. Thanks, Simone.
Thank you all. Bye.